You know what frustrates me? The fact that we can't just set a date and have the switchover for all cars go automated. Starting tomorrow, no human drivers, right? A national or global fleet, some sort of mesh network kind of thing, centralized, decentralized, I don't care. Just make them all automated all at once. Why is that better? Well, it's going to be safer and much easier to control. Safer primarily because there are none of these lunatics named human beings on the road doing all types of weird maneuvers. The machines will drive for the most part predictably, and when they all do that in concert, it magnifies. Not to mention the opportunity for things like an entire highway to just clear one road for a ambulance to get through all at once in a coordinated, optimized, efficient way. But I realize we're not going to ever get there. The only way automated vehicles are going to work, at least in the short term, is if there's some sort of hybrid model. Human drivers and automated drivers together. But even if you take the people out of the car, you've still got people on the streets. And human beings are as unpredictable on foot as they are behind the wheel of an automobile, maybe more. Has anybody stopped to model out how self-driving cars can look precisely at pedestrians? This week on the show, we've got Arash Kalatian, a PhD student working on problems exactly like this. We'll have all that and more right after the break. I want to give a special thanks to Nathaniel Judge, who you could follow at SpurskyJudge27. See the show notes for that. Thank you so much for being just one of the respondents participating in our listener survey. We're going to send you a free t-shirt, but the survey's not over yet. If you haven't already done so, please make sure to check out dataskeptic.com/survey. We'd like to get your feedback on the show, so thanks in advance.
My name is Arash Kalatian, and I'm a PhD candidate in transportation engineering at Ryerson University in Toronto, Canada. My thesis that I've been working on for a while now is in general about the interactions of humans and autonomous vehicles, and the particular paper that I guess we are going to discuss today is part of that thesis.
Before we get into that, tell me a little bit more about what transportation engineering entails.
Okay. So let me talk about the way that I started transportation for that. Basically, I started as a civil engineering in my undergraduate, and then soon I realized that it's not my thing. I did not, as a classical civil engineer, I was not, the mathematical parts and the novel parts were not satisfying to me. I decided to pick a field in civil engineering, which basically tries to understand how urban areas and how the transportation of the urban areas is working. So it's part of the civil engineering basically, but it's more in the other things that is involved in that are like industrial engineering and urban planning especially. And in recent years, the massive data that are available especially in transportation. So there is more a shift from the classical civil engineering part and classical statistical parts to more data-driven and more data science-y approaches.
Absolutely. Well, when most people talk about self-driving cars, I think the sort of obvious or the aspect of that has the most sex appeal perhaps is doing the actual automated driving, getting into TensorFlow and LiDAR or computer vision stuff and driving that car. But your work is sort of adjacent to that. Would that be a fair way to describe it?
Yes. So there are so many parts in developing self-driving cars, from the technical parts, as you mentioned, the visual parts, the object detection parts, and to some even legal parts that involve how these self-driving cars are going to do legally and how we can change them. But in particular, the part that I'm interested in as a transportation engineering is the interactions of these cars with pedestrians, as pedestrians are considered as the most vulnerable road users. And already there has been some instances of autonomous vehicle and pedestrian collisions. Probably the most famous one is Uber's test drive autonomous vehicle fatal incident in Arizona. So we decided to take that part, the interactions of the self-driving cars with pedestrians who are trying to cross the road, and in particular, the pedestrians who are trying to jaywalk. because when we were reading the reports of the organizations on the investigations of the Uber incidents, we realized that one of the reasons of such accidents is that they do not pay the required attention to the jaywalking pedestrians, simply because in their data, this kind of crossings is not that common. In North America, jaywalking is not that common. But although it's not common, if something happens to in a case that is related to jaywalking pedestrian, outcome would be disastrous. So we try to focus on this particular part of the self-driving cars.
So from a self-driving car's point of view, it's observing or hopefully observing a lot of different objects. Certain objects, like let's say a bouncing ball, they're going to follow physics pretty well, so maybe there's a good chance of predicting them. People, on the other hand, are going to do all manner of different things. So it seems like not that you're playing chess between a pedestrian and a vehicle, but there is a certain degree of unpredictability there, I guess. What steps do you have to take to model the behavior of a pedestrian?
Exactly, that's true. There is a natural chaos in the behavior of pedestrians that we would require special attention to the modeling. So we have divided the pedestrian behavior in our projects in two parts for the jaywalking pedestrians. First, the pedestrians is waiting on the sidewalk. They wait to start crossing and they decide to, or maybe they decide to wait longer. And then after the intention is clear that they decide to start crossing, they will follow a trajectory. So these two parts will be observed by the self-driving cars. We have made the distinction between these two parts. So we are doing parallel research on the both parts. This paper that we are talking about today is on the modeling of the waiting time, the time it takes for the pedestrian to start crossing. And for that, we have developed what is called survival models, which is basically trying to predict the probability of an event occurs and try to estimate the time before an event. And in our case, the time would be the start of the cross by the pedestrian.
And just a small point of clarification on terminology. These survival models, we're not talking about the survival of the pedestrian, are we?
No. So survival models, the terminology, the survival models are firstly developed in medical sciences. And that survival means the survival of the patients from an illness. But in our case, the survival would mean a totally different thing. We are talking about the time it takes for the pedestrian to start crossing. So that will be the survival, which is not a correct word in this term, but it is the name. So it's the survival here would be the probability that the pedestrian stays on the sidewalk and not starts to cross.
Ah, yes. As you said, it's really the event is the starting to cross that we're predicting.
Exactly.
And what made, so I'm not an expert in it, but I'm aware of those sort of hazard curves and things like that and how that emerged from the study of disease. What gave you the insight that that might be applied to something that on the surface is different, a person crossing the street?
Before this project, we were doing another similar project. In that, we were considering the behavior of distracted pedestrians who were looking at their phones or playing some games on their phones while they were crossing. And we developed different models based on that. We started from simple models and went to models to survival models and different survival models. In that case, it appeared to us that hazard functions, Cox proportional hazard functions in particular, was the model that for our type of data, which is basically a virtual reality data set that we may talk about later. For our type of data, survival models were performing better than the other models.
Very interesting. Yeah, let's get into that data set. What is the nature of the training data set you have to study?
We have developed a virtual reality experiment. In that experiment, so basically participants would wear some headsets and they will find themselves on a simulated road in which we will ask them to start crossing the road whenever they feel it is safe or it is comfortable to cross. Meanwhile, it's an interactive environment. So if the pedestrian starts crossing and if they give the virtual cars enough time, the cars would slow down for them. And in that environment, we have self-driving cars, virtual self-driving cars actually, and human-driven cars, etc. So That was the idea of this virtual reality thing. And the reason that we started with virtual reality was that such experiments that requires pedestrians crossing the road might be so dangerous if we want to do them in an uncontrolled environment, because we wanted to see the effect of different parameters on the behavior of pedestrians. And we cannot just ask pedestrians and participants to start jaywalking in an uncontrolled environment because simply they might hit a car or something like that. So we tried to make experiments controlled so that we can play with the parameters. We can change the speed of the cars. We can change the traffic. We can change the design of the streets and see how different people would behave in different conditions. For such cases, basically questionnaires and stated preferences surveys are used, which are basically asking people how would you react if you were to confront such a situation. But we thought virtual reality can be a good alternative to that. And it gives us a notion on how people would actually react if they have something similar to that on the real road. That was the reason that we switched to virtual reality. And we did our experiment last summer and over a 5 months period. In total, we had around 180 participants. Each of the participants did the experiment 30 times. And while they were doing this experiment, we would be recording their behavior. We would be recording their speed, their movements of the head, their coordinates, and their acceleration, and even their stress level, if they feel stressed or if they feel comfortable when they are crossing. By collecting this data, we also could calculate some other information like the trajectory of the pedestrian or the wait time of the pedestrian. So that was how we started using virtual reality and the data set that we had.
It seems like actually you might have a deluge of data because you have so many different signals from the pedestrian. Not to mention, I guess, you could take a video of the experience they're having in 3D as well. Do you use the data at its most raw level, or do you need to transform it in some way to make it more useful?
Well, of course, basic transformation. I'm not sure if I should call them transformation or basically data cleaning, but the raw data requires some simple data cleaning. But other than that, no, it can be pretty straightforward to use that.
I can definitely understand why VR is a good choice. You might have a hard time getting a medical ethics board to say you're allowed to ask people to step in front of cars at the last minute. But at the same time, VR isn't the real environment. To what degree do you think that separation can bias your data?
That's totally true. And I should note that as a transportation engineer for such studies, at first, our priority would be to describe our data, to the model to be descriptive and maybe prescriptive. So we want to suggest the government or the city planners or the decision makers some ideas how to change the dynamics of the road and how to make decisions. At first, the priority is not for the autonomous vehicle manufacturers to use such data for their cars. We want to suggest policies. And for that, we need to observe the behavior of the pedestrians, of the people. And virtual reality in that case can give us good result representation because we are having this environment, and when we change some parameters, people would react to that change in that very environment. So it might not be a good idea to transform the data for self-driving cars because that might not be realistic to train autonomous vehicle on such data. But at the same time, we can use this data to see the changes in the behavior of the participants and how one single participant would behave differently when confronted with different scenarios.
Thanks to this week's sponsor, Terminus DB. By the way, I hope everybody is staying at home and staying safe in this time of seclusion. But your work or learn from home experience during this time of COVID-19 is a perfect opportunity to develop a new skill, learn a new technology, and extend your resume. I'd like to recommend you put Terminus DB at the top of the list of things you're considering. Terminus DB is an open source, model-driven graph database. Now, graph databases are cool enough on their own, but on top of that, Terminus DB has some additional features that make it an extremely powerful tool for data management. Think of it like Git, but for data. And in the same way that DevOps has had a huge impact on software delivery, DataOps is going to be impacted by Terminus DB. It makes it possible to collaborate, it provides CI/CD tooling, and a great suite of tools for data management. Using Terminus DB, you can branch and merge your data just like you do in Git. You can do data rollbacks and even time travel. So if you have really challenging analytical needs in your organization or research, see if Terminus DB is the right tool for you. Learn more at terminusdb.com, or as I'm about to do, I recommend you guys go over to their GitHub page, github.com/terminusdb. They have a bunch of the projects very nicely pinned and set up. I'm going into Quick Start, and I'm going to star it so that I know that anytime there's an update, I'm going to hear about it. Why don't you guys consider doing the same? This is a really cool open source project, and the community around it is developing very nicely. terminusdb.com. Do you have any takeaways about the types of situations or environments that affected the pedestrian? I guess what are some of those policies? Are there safer streets or safer recommendations you guys discovered throughout this work?
Yeah, exactly. So the results that we obtained from the model had some interesting insights. The first one was that while pedestrians were confronting fully automated conditions and self-driving cars, they would wait significantly longer than when they are confronting normal cars and human-driven cars, because they feel more in danger, kind of, and they had to wait longer. So it makes sense because they are not used to that at first. What we would suggest with our paper to people who are in charge is that to have some nationwide educational training programs to familiarize pedestrians with the new dynamics that are going to be ruling the roads. And that was one thing. The pedestrians would wait longer in fully automated conditions. The other things that are more related to the city conditions, we showed that when we have narrower lane widths, when we have lower traffic densities, and when we have better sized dances, pedestrians would wait shorter time. So these are some changes that actually can take place in the cities. So there are suggestions to increase the width of the sidewalk and decrease the lane widths, for example, in Toronto, or to have better equipment for the lighting of the roads. These are something that we showed that actually matter on the experience of the pedestrians who are trying to cross the road. And also, aside from that, we showed that people who actually had walking habits, who were, for example, commuting to their work walking, or who did not use a car, or who used public transit, they had better experience in the data collection. They felt better and they felt more comfortable crossing the roads in the presence of autonomous vehicles. So we would suggest to promote active modes such as walking, bicycles, and suggest to develop more pedestrian-friendly infrastructure on the roads. And these were the main takes from the data. Other than that, the other interesting thing that I confronted when I was doing the experiments was kids that were trying to do the experiments. Part of our data collection campaign was done in summer schools that involved a lot of kids. And we asked them to do the experiments. And we clearly could see that they made the situation for the self-driving cars like a game to themselves, because they knew that the cars, they saw no driver in the car, and they knew that the car would stop and slow down for these kids. So they would play a game. They would go in front of the car, make the car stop, and they will go back and do that again and again. So these things are things that needs to be addressed, and that actually can happen in the future when we have the self-driving cars with no drivers, when some people do not feel bad to just to walk and do not care about the outcome. So these are the things that needs to be addressed via educational programs or whatever other tools possible before the self-driving cars come into streets.
I'm curious, as you look through the data on the participants in the study, how much variance do you see across pedestrians in terms of their behavior, right? Maybe some people are aggressive walkers or passive walkers.
We collected socioeconomic information from the participants who were doing the experiment to see the differences in the behavior of different people. So, for example, we realized that people who were aged over 50 and they would require more time crossing as it is expected. Or the people who had tendencies and who had walking habits, they would feel more comfortable and they needed less time waiting on the sidewalk. This kind of variations was observed, but there were so many variables that appeared not to be important. For example, we didn't find gender as a deterministic variable in our case. Female and males had the same behavior. And I would say the most significant difference among the variables that we collected were the variables that were related to commuting habits of the people. So roughly we can divide them by people who are used to walking and who go for walks for their shopping or for their work or whatever, and people who do not. So this difference was the thing that I would say was the most observable thing among the differences in people among the data that we had collected.
So it almost gets back to just practice. People who are used to walking are maybe better attentive to their environments. Could that be the conclusion or a conclusion?
Yeah, exactly. A conclusion, yeah. Other than that, we collected age, we collected the education, we collected the data related to the income and this kind of things. And none of them appeared to be, at least based on our results of the model, none of them appeared to be the significant factor. So among that variables that are related to people promoting walking habits and promoting active modes of transportation seems to be the one that is affecting the behavior of the pedestrian.
Well, you'd mentioned how this might culminate into some recommendation to, I don't know if it's city planning people or landscapers or architects, but to inform the people who make the choices that could affect health and safety in this regard. Those people might not have a machine learning background, so it would be great if there was a degree of interpretability in your work. Could you talk about some of the ways you address those sorts of needs?
Yeah, so the thing is that traditional CPH model, traditional Cox proportional hazard model that is used as the baseline model in our work, and all the old school models may not have the exact and may not have the best performance in prediction, but they give us more insight than neural networks in terms of the model interpretability. So as you know, neural networks and most machine learning models are assumed as black box models. They get input and they just give outputs and without knowing what is happening inside. By using our model, we could increase the performance of the model, of the traditional model, by 5%. But the question came in mind that, okay, now we have increased the performance, but we cannot use any of this information now because we do not know what is happening. We just have put some data and we have just got some results. So that's why we had to do some interpretability models, for which we started with SHAP model, which is basically a model agnostic post hoc algorithm. It means that it just doesn't care about the model that we are using. It just considers the input and output of the model and tries to give us an estimate on how different factors and different features are important on the output.
Gotcha. And is that how you arrived at some of the conclusions we discussed earlier about the results and the impact of the variables?
Exactly. All the conclusions are based on the SHAP values.
Just to unpack SHAP a little more, there are other techniques you could have applied, just sort of traditional machine learning, things like accuracy and feature importance. What made SHAP maybe of extra value that those methodologies didn't deliver on?
Yeah, one good thing about SHAP that made me use them was mathematical background and game theoretic background that it has. So not all of them, but most of the other models are basically trying to somehow simulate the results, and based on what is happening on the model, they try to give us some idea. But SHAP has solid mathematical proof that can be used if you want to present your work and if you want to give advice to a government or to a decision maker. You have some mathematical proof of why SHAP actually works. That was one reason that we decided to use SHAP. The other reason is that thanks to the creators of SHAP, they really have a really nice GitHub source code. It's really easy to use, and I really liked working with that. I tried different things, and I realized that SHAP, the way that they have provided the source code and their model was something that was easy to use, understandable, and giving understandable results. There were two reasons, and the other reason, unlike other works in transportation mainly that use interpretability, the good thing about SHAP was that it considers the fact that contribution of a feature depends on the values of other features. For example, feature permutation methods just one variable, and they assume dependence in all the features, but SHAP does not do that.
So one of the very interesting aspects of your guys' research was identifying this event, this decision to cross, and that even though the trajectories and whatnot can be modeled after that, that is such a kind of important way to summarize this potential conflict between a vehicle and a pedestrian. Are there equivalent events, do you think, on the car's end of reaction time, of, signals you're going to get from pedestrians one day? I know that won't apply to automated vehicles, but is there a side of this that could be interesting from the driver's point of view?
Yeah, actually, what I'm trying to do right now in my research is to apply the model to other datasets, which are mainly the video datasets, the open source video datasets from Lyft or Google or different companies that they have. And I want to see the exact same thing from the car perspective. So we considered our model on virtual reality data, which is useful for decision planning or other transportation purposes. But we want to apply the model from a self-driving car perspective and use the video data and actually use the data that they can observe to try to predict if a pedestrian starts crossing or when they will start crossing, and if they start crossing, what would be the trajectory that they will follow. So that would require a change of the perspective from the virtual reality data and from the transportation perspective to a car eye and to the vehicle eye to see how they would see the dynamics of the city. And based on that, the car would be able to predict and decide if the pedestrian wants to cross and how they would cross, and then take the required actions. And based on what the vehicle observed, they can take required actions.
Makes sense. And of course, this is a challenging problem and an unpredictable one. So I can't imagine you'd get anywhere near, 99% accurate or anything like that. But could you talk a little bit about what metrics you are optimizing towards and the results you're seeing?
Yeah, so C-index is the measure of accuracy in the survival analysis. So it basically tells you if you predict that a pedestrian with the specific features and in specific conditions, if you predict that pedestrian to have a shorter waiting time than another pedestrian with specific parameters, if you predict that the first pedestrian has a shorter waiting time, would that actually be a shorter waiting time in the real data or not? So if that's the percentage of these correct predictions on who starts crossing first would be the global index that is used to compare the performance of our model. And we used the index to train our model, and we could increase the performance of the model from the traditional model by 5%.
I hope that research like this continues and starts to inform policy choices, much like where I think you guys are going with it. If by chance there is a policymaker listening or somebody knows someone and intends to forward this, do you have any advice on the best way people can get key takeaways for, not that it has to be low cost, but it seems like there could be some low cost, low hanging fruit here that could save lives? Where should people get started learning about things? I guess they can start with your paper, but do you have any advice in general on how someone would get into these details?
Yes. So as a transportation engineering who is working on the pedestrian problems for a while now, I've noticed that there is a lack of research and lack of concentration on the pedestrian side of the story. So there are so many works on the self-driving cars, and there are so many good works on the technical terms, in the object detection terms, on paper, and the technical terms, we are doing great. But about other, and especially more vulnerable road users like pedestrians and cyclists, there is not that much of a concentration. So I would suggest to take a look at that side of the story and consider these road users, pedestrian road and cyclists, and especially kids and seniors more carefully. And for another suggestion that I would go with would be the use of virtual reality for educational purposes for such cases. So, of course, we do not have autonomous vehicles on the road in large scale now. So if we want to present them, that would be a total change in the dynamics of urban roads. So by using virtual reality as one of the possible tools for educational purposes of people, especially pedestrians and maybe even the passengers on the cars, I would assume that that would be a really useful tool to start with.
Absolutely. Well, I agree. I hope there's more research in this area. I'm often a pedestrian and my wife is a very frequent cyclist, so seeing a little bit all-encompassing work is very inspiring, and I hope this leads to some interesting policy choices. Well, we've talked a little bit about where your research is headed next. Maybe you could share a few more thoughts and also tell us where can people follow you online.
So next step, it's basically my thesis project. So the next step that I'm working now is applying the models to the data from the self-driving car sites, and I'm using the video data from Google and Lyft to extract them and extract the pedestrian sides out of them and try to work and develop the models based on them. And I'm also working on the trajectory prediction of pedestrians. And finally, it will be a framework for investigating the interactions of humans and autonomous vehicles. I post my updates on my website. I will send the address to you. It is arashkalatian.com. I'm also active on Twitter.
Excellent. We'll have links to those things in the show notes as well. Well, Arash, thank you so much for coming on and sharing your work with the audience.
Thank you very much.
Thanks for listening to Data Skeptic Interpretability. Our guest this week was Arash Kalatian. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich. Thanks for listening, everybody, and make sure to look both ways at least twice.